to talk to me, which I highly doubt, you can always text me. Okay. And good luck, Julie. You'll do great.
Thanks. Thank you, Suzanne.
You're not supposed to tell her she'll do great in advance.
Oh, is this Tim?
Yeah.
Are you in Juneau?
I am.
Oh, I'm so jealous.
Otherwise, I'd be in your office.
Yeah, you guys have to have a beer and think of me tonight.
No, nobody at the commission knows that I'm in Juneau. I just said I'm working remotely, and they'll figure it out later. Because I can't be fired for me.
Okay, so now I'm seeing a blank screen.
Yeah, me too.
Okay.
Am I supposed to?
I'll get Chris. I think. Oh, and that is.
There's another.
Is that Beth?
Another random person. Must be Beth. She's waving.
Okay. Excellent. Excellent. All right. I'm gonna go get. I'll go get Chris.
Is that like our neutral?
Yeah.
Do you do that at this university system?
What's that?
Do you have like the neutral referee? From the
Yeah, we have an outside examiner. He's calling in from Fairbanks. I didn't know in the Canadian system, your committee's called opponents.
Oh, your opponents?
Yeah, your opponents. It's not your committee. They're called your opponents. And they wear the commencement regalia. So the gown that you wear at graduation, they all sit in the graduation regalia, and they're called opponents.
Wow. And in Coimbra, in Portugal, the old like World Heritage Site thing, their defense is a defense theater. The committee gets these giant chairs up on a platform, like gladiators. The graduate student is down in a pit all by themselves, and then the audience is in this circle. It's like this crazy Roman amphitheater.
Yeah.
Like you just drop them through the hole to the lions if you don't think they, or you just flood them.
Yeah.
Oh, hey, remote sites, can you see us, the camera and the presentation now?
Oh, okay.
Okay, I can see a dorky picture of Julie on a boat.
Say that again?
Reduced in my capacity at the end.
I can see a picture of you on a boat.
Yes, that's it. That's perfect.
And I can see you guys in the corner, so I'm all good.
Okay, good.
And now it sounds like you guys muted something. I can't hear you anymore.
Yeah, we muted the room until we're about ready to start.
Variably, there are a lot of people.
Okay, it sounds like one of the guests is not muted, but the room is muted. Is that possible?
Yeah.
Oh, so
But that's what 1 year I'm not.
so Beth, is that you? Can you is with the dog barking? Or there's a dog barking?
I've been saying my greatest hope for the end.
I know there's probably a mute button, but where is it?
Oh yeah, let's see.
So Beth, it's on the bottom of your screen. On the bottom of the screen, there's a very left-hand microphone symbol, and you click on that to mute.
Okay, good.
That's one of the entertaining things is that 4 or 5 years ago, we did not have Monday sessions at all. On Monday.
You do not want to be dehydrated.
lost all the science. We'll hear about major science and we get some scientists that are terrible agenda. How would we do that? Decisions, but we don't have unless we start on Monday. So now we start on Monday.
Would mean you're traveling over the weekend.
Travel over the weekend. Still don't have any science presentations. So they added another half a day of assessment deliberations. Never put the science back on the agenda.
Well, how does that work for people like Balsinger? Because he's furloughed, right? Is he with Noah?
He's with Noah. He has stepped down as president. But it's the same thing. We had another one where there was a government shutdown very close to the date.
Yeah, so they changed it, yeah, because there was an issue with that. That was the only for sure. Okay. Yeah.
Oh, my friend Carla reminded me, I wasn't checking my email for a while, and yes, I meant to go to that.
Yeah.
Oh, good. Brave the snowstorm.
It's potential we could end up with the enforcement reports because Coast Guard is still essential, but whether or not this would be considered an essential function is highly questionable.
Chris?
So,
Oh my goodness, hi Chad.
so we will see if it's still shut down in 2
Let's hope
right
not.
now. Let's hope not, but right now I don't think you're like the other stuff.
Yeah, it's not looking very optimistic.
Of course, on NPR, there was pretty sure he was a senator.
Seems a prematurely terminated.
That's some insight.
Not to
That was also before the 5-minute walkout discussion. You need to walk.
It's not
Right.
It doesn't sound right.
Are you doing your hands right now?
Yeah.
Yeah, it's all done today.
Yeah.
Yay.
Yeah, I didn't even know it was an option, but Andy's down and things up, so.
You've been harassing you for ages, and then it's like twice a week.
I think that I have done that already.
Not about that.
6 years.
Yeah.
Right, it's okay.
Thank you.
It's okay. Man.
How's it going?
Amanda,
I know.
how are
Been
ya?
good, long time no see.
Long time.
Daphne.
Yeah, nice to see this full circle.
I know.
Not that I was there at the beginning of the circle.
Hey, I'm glad you didn't make it.
I'm so excited. Yeah, you look beautiful.
Thank you.
Decided to hop on the ferry
You
yesterday.
alright? We need to go outside and do some push-ups.
You mind if
I'm here.
That's what's
Yeah.
happening.
All the beds.
Yeah.
Normally be skipping
Are you gonna
work.
stick around for
Oh, I don't.
I am, like from right over there, to see this.
Yep.
I'll be there.
You're in the same boat.
Oh, that's
I
what they
know, a friend
normally
of mine
do.
reminded me.
Oh, yeah.
Like, oh my God.
It's coming and seeing.
So which date?
I got it handwritten on the calendar.
I just throw this out. See how you fit on
Back,
there.
I brought home, but I couldn't look at it. It's been in the
Oh,
bag.
that's a good idea.
Misappropriation of federal property.
Not sure I know.
Is that are you allowed to? Is that misappropriation of federal property?
It is,
Yeah.
yeah.
There's
Definitely, and there's a
Yeah.
number. It is.
You know, files.
Okay.
Because I'd say.
That's true.
Yeah, okay.
See, but normally when they have like the seminars here, and those guys all.
Yeah, I
talk
gotta
over
remember
here.
saying that.
They're even remotely interested.
Unless you're,
Yeah. This is all
Yeah,
right.
yeah.
Okay, sit in the back. I'm not gonna be the front over here. Okay, thanks.
Oh, Nikki's right behind you.
I'm here.
The safety class is C.
Oh, hello, you break the snow.
It's our fault. Dave?
Hey, how are you?
You did.
I know David's.
Hi, Nikki. How are you
Hi,
doing?
Nikki.
I don't do it, man. He was gonna retire that. If Davis here.
Dude.
Kind of retire because he kind of looked at it.
They're pretty mellow this time of year.
Yeah. It's
No.
And you can't
Is
smell
he,
it.
is he retired?
Day to day.
That's a
How many
bummer.
say there a year
It's probably.
Well, eventually he'll be retired.
Yeah,
But he's not working.
That's
But
a
it's-
pleasure day.
Maybe twice
Oh,
that.
day for the one that was-
Yes.
Yeah, it was beautiful. That was,
like that.
Oh, really?
Hey, time to
It's not like that often.
Central New York, south of Syracuse.
Yeah. Yeah.
Where are you going, Doug?
Nice day. And I was looking forward to that. We had the board in the room.
Were your parents here?
No, my dad was a
Another person who I haven't seen in a long time.
Jennifer Mondragon.
with the band.
Yay, I'm glad you made it. It's gonna happen, guys.
Oh, we only need one. Yeah. You'll wear me out.
How long are you?
I got a good light. I don't. They're gonna find it.
Oh, good.
She did email me.
You know, it is all.
Because I always get, she, you know, for you. That's what you like?
I know
Red or beer? We have beer.
I'll be it.
Oh my God, that's good.
How many years?
All right. The lake should be nice. Just like the other. Yeah. All because you. He's brought the average up.
Actually, we've got rain cleared on Twin Lakes.
It's way fast because it's fast.
We'll wait for like maybe Then which one do you think are next to Empress?
That's when I.
Okay.
Yeah, right before I get to Suzanne's on.
Yeah, she's the one
Yeah, grassland piece. We did this.
All right, I think we'll get going now.
Are we on mute?
No.
Okay.
Can you hear me at the distance sites?
Just the, okay, good. Okay, good.
And is the outside examiner mic on here? Okay, great, thank you. That's good. Okay. I'm Andy Seitz. I've had the pleasure of working with Julie over the last 9 years as her advisor for this journey, and I thought I'd give you a brief introduction about Julie to familiarize you with her. I'm sure most of you know her pretty well, but Julie grew up in Oregon, and she went to Oregon State where she got a BA in liberal studies. And this is really interesting, and this is going to tie in later to Julie, but she is, if there was a female counterpart to MacGyver, Julie Nielsen is it. So Julie first got a BA in liberal studies and studied Russian language and history and international economics, which is sort of on the opposite end of the spectrum from what she did her PhD on. And then she moved up here to Juneau and got a BS in biology at UAS, and worked in a variety of technician and biologist and researcher roles in a variety of different animal groups. Shortly after that, she got an MS in fisheries from UAF and studied crabs as part of that. And then she continued this sort of broad experience in different employment fields. And she worked for groups like Fish and Game, USGS, UAF, and then she started her PhD in 2010. And I was in my second year as a faculty member, so Julie and I have sort of co-evolved together through this project, which is kind of fun to think about. Julie did her field work in Glacier Bay. Here's a typical picture of beautiful Glacier Bay and its glassy calm. And this is at Julie looking at the light at the end of the tunnel right there, which is happening today. But as I said, Julie's the female counterpart to MacGyver, and she assembled this this crew of people to help her with her field work in Glacier Bay. And here's Tim, who had an Italian name for that picture as a Venice boatman, and I can't remember what it was. But anyway, here's Tim, another graduate student, and then I believe this is the Park Service staff in the skiff. And so this was part of the crew that helped her out. And then here, she even got Alan to help her out. So here's Alan doing some prep work, getting the boat ready to go over to Glacier Bay. And then here's MacGyver in action here. This is Julie fishing. She did all steps of the field work and with gusto. This is Julie getting all the long line hooks ready. And then this is my favorite picture because Julie has her game face on here. And you know, normally Julie's pretty smiley and happy, but this is Julie when she really gets down to the nitty gritty. And I don't know what she's doing, but there's a lot of cool things like pop-up tags and then glider bodies that are attached to other cool things here. And then here's Julie with many things happening. The boat that Julie did her field work on looked like the USS Enterprise in Star Trek by the time she had it all outfitted. And so here's Julie doing some tracking work. And then here's Julie she even turned into a surgeon and did a bunch of fish surgeries. And we all sort of got out of the way as Julie implanted archival or acoustic tags in these fish. When Julie's not doing her fish research, you can find her on the hockey rink. And so here's Julie faithfully annually made it up to Fairbanks for our Shinny Ice Hockey Classic, where we all got out and tried to keep our teeth in our head and not hit each other with sticks. And so these are a bunch of Fairbanks-based students, and Julie is here. And then Julie is also a world-renowned cellist. And I didn't have any pictures of her in concert, so I made my own picture.
Look at that technique.
Yeah, and she's got beautiful technique here. And then, and so, you know, looking at the light at the end of the tunnel, Julie's almost done her PhD and moving onward. She has her own consulting business that she established and she owns, and she specializes in exactly what she did for her PhD, and that's fish telemetry and movement data analyses work. And she has this business up and running and has contracts and is moving forward. And so with that, we'll turn it over to Julie, and she can tell you about the last 9 years of her life.
Oh my God. Okay, well, thank you, Andy, for that very nice introduction. I'm going to talk to you today about my PhD research on the movement of demersal fish in Alaska. But first, I'd like to take a minute to thank Andy for being an awesome advisor. And I'd also like to thank my committee members, Milo and Franz, and Tim Lower came up from Seattle for from the Halibut Commission. And we also have Suzanne McDermott tuning in online from Seattle. She's from NOAA. So thank all of you for your help over the years. It's been amazing. And also, before we start, I want to thank my funding sources. I had fellowships from the Rasmussen Fisheries Research Center and the PCCRC that really financed the bulk of my studies. And then I also had funding from the Park Service and from the North Pacific Research Board and the UF undergraduate research program. So all of those funding sources really can make possible what I'm going to talk to you about today. So demersal fish species in Alaska, such as Pacific halibut, Pacific cod, and sablefish, are all really important. They're high value commercially, ecologically, and culturally. And we know from conventional tagging that they're capable of making really long distance movements, thousands of kilometers during ontogenetic and spawning migrations. And so partially because of this, they're managed on large scales with the assumption of open populations. But in recent years, there's been some evidence from electronic tagging and genetics research that suggests that perhaps there is more spatial structure in these populations than we initially thought. And spatial structure, understanding that is really important for management. For things like stock assessment and delineation, understanding connectivity and whether or not metapopulations are important, are really important. And then also spatial distribution of fishing effort. Is there potential for local depletion that you need to be aware of? And also it's really the basis of space-time fisheries closures information, whether you're assigning timing of seasonal closures or you're designing a marine protected area. So this information, detailed information, is really important, but it's difficult to get. It's difficult to get for demersal fish, and especially with conventional tagging. They're a coarse tool. And so my goal with this dissertation is to come up with methods for obtaining detailed information using electronic tag data. And the focal species that I'm going to be talking about is Pacific halibut. So for an overview of the dissertation, all of the 4 chapters, they're all talking about movement at different scales in space and time, but they've all, they illustrate the importance of understanding movement at both small and large scales for a migratory fish. So for chapter 1, we're looking at fine scale movement during the summertime, summer foraging. And in chapter 2, we're looking at more of an annual movement pattern relative to marine protected area boundaries. And in chapter 3, we're going to introduce a geolocation model for demersal fish that can be used to look at multiple scales. And in chapter 4, we're going to be introducing a potential new geolocation variable that may assist with geolocation. So for chapter 1, this first chapter involves characterizing the movement of adult Pacific halibut during summer using acoustic telemetry and the net squared displacement statistic. So we began in the year 1991. This was the year the Soviet Union. It's crazy, isn't it? It's also the year that Point Break. And Michael Jordan brought the Bulls to their first ever NBA championship. And so while he was wowing the crowds with his moves, Philip Hugi and Jim Taggart were putting the first ever sonic tags on halibut in Glacier Bay. So why were they doing this? Well, at that time there was some talk about fisheries closures. Either some part or all of it might be closed to commercial fishing, but there was no real biological rationale at that point, meaning one strategy for designing a marine protected area is knowing that it's going to contain the movement of all your fish, but that information was not available. So that is the basis of this study, is they wanted to understand the movement patterns of halibut in Glacier Bay. And then when I inherited the data from my first chapter of the PhD, my analysis goal were to identify movement patterns from the data and also quantify spatial scales of movement. So, and this is zooming into the study area in the center of Glacier Bay, and all the yellow circles are where the fish locations were. There were 43 adult halibut tagged during the summers of 1991 to 1993. The study went longer than that, but I just chose the first 3 years because there was more tracking effort at that time. And there was manual tracking of these fish. It was irregular at scales from daily to weekly, but an average of about 4 days in between observations. And so when I went to analyze these data, I needed a method that was robust to missing data, and so I chose the net squared displacement statistic. And the idea behind this is that your displacement over time tells you something about behavioral patterns such as foraging or migrating. So for example, if your displacement over time increases linearly, that's associated with random movement such as foraging. And so it's a linear model with slope giving you information about diffusion. And so the analogy here is just to imagine you're blueberry picking and you're just over time moving farther and farther and farther away from your car. So, however, if you have a home range, your displacement over time is going to be flatline. There's no relationship with time there whatsoever. And so that can be modeled with an intercept-only model. And then that intercept gives you the information about the spatial scale of that movement. And so the analogy to this would be just doing some gardening where you're moving around the house but not really going very far. Okay, so another property of the net squared displacement statistic is that when you make directed movements, it has an exponential form. And so you can model a home range shift by, there's a flat line where you're at in the home range, and then when you start to move, it becomes exponential, and then when you reach your new location, it flattens out. So you can fit a sigmoidal curve to this. And then that gives you information about the spatial extent and also the timing of this movement. And the analogy here is just shifting your household goods from one place to another. It can also be used to determine if a fish leaves and comes back somewhere. And so this is just simply a double sigmoidal curve. You can fit this to find the spatial extent and the timing of this movement. So this is a temporary journey. The analysis here is a vacation. You're going somewhere, but then you're going to come right back to the snow. Okay, so to identify patterns based on these principles, you take the displacement over time data for each fish, you fit it to each of those models, and then you find which is the best model based on which one has the lowest AIC value. And then to look at spatial scales, you group together all those ones that had similar, had the same movement pattern, and you fit a mixed effects model to these. And that allows you to find a population estimate. So the average overall estimate for home range being the, so that's the intercept, and random is a slope of a linear line, and then site fidelity gives you your estimates for timing, speed, and spatial extent. And so here are some of the results from this. So I'm showing on the left here some examples of home range movement patterns here. Each yellow triangle is a fish release location, and then each colored line is an individual fish. So out of 32 fish that had enough data to characterize the movement patterns, 17 of those were home range. So, so no increase in net square displacement at all over time for those fish. Site fidelity was the next most observed movement pattern. And then shifted home range. So there was 6 for the site fidelity and 5 with the shifted home range. And then random, there was 4. So, and in terms of the scales for the home range, in order to interpret that statistic, you take the square root, which gives you like a radius estimate of movement for the home range. And that population mean was 401 meters for home range size. But the range from the individual animals was 100 to about 1,500 meters. For the random movement pattern, and so for this, the slope is approximate to diffusion. We came up with an estimate of a diffusion coefficient of 0.9 kilometers squared per day. And for the site fidelity, which we interpret in the summer as forays to a different part of the bay, we had a spatial extent of 10.5 kilometers and an average duration of 40 days. So in order to visualize those results a little bit better, the 400-meter radius is basically your average downtown Juneau. And the 100-meter, the smallest one, is the size of Harris Harbor. And then on the larger end of the home ranges, it's more like Mendenhall Lake. So, to conclude that, the net square displacement statistic was a valuable approach for describing movement patterns and scales. It was good for irregularly spaced data, and it provides information in the format that you can use it in larger scale models, which we'll get to later. What we found was a predominance of non-random movement, site fidelity and home range, and small home ranges. And we also discovered the ability of the fish to return back to that previously occupied home range. And this behavior is, it's not that much different from lingcods and some rockfish species. It was surprising to find that they had such limited movement during the summer. And now we know, since the marine protected area has since gone in, that it would likely contain the movements of these tagged halibuts during the summer, since their movements are so much smaller than the boundary. But this was summer, and we don't know about winter. In winter, they might take winter spawning migrations and leave the bay. And so in order to understand effectiveness, you have to understand what they're doing year-round. Do they leave? And if they leave, do they come back? And that is the subject of Chapter 2, which is looking at annual movement relative to marine protected area boundaries. So now we're in year 2013, and in 1999 they made Glacier Bay a marine protected area, and commercial fishing was phased out north of this boundary at the entrance here of the bay. So in 2013 we went back to Glacier Bay with the goal of looking at revisiting the summertime movement with acoustic telemetry to see, okay, is it still the same as it was 20 years ago? And then to expand that and to look at more annual movement and look at things like seasonal displacement from summer to winter and for a full year, and also look at continuous residency or migration from the marine protected area throughout the year. So we were trying to see if there were spawning migrations, and if so, did they return to Glacier Bay. So now we're zooming into the study area, which is in the central part of the bay, and the release locations of the tagged fish are shown in the yellow circles. There we go, there's circles there. And also in the study area, it's about a 5 by 5 kilometer study area, that we had an oceanographic survey station from the Park Service where there's CTT drops. And then there was also a stationary mooring that collected continuous data on temperature and depth. And so we put out 25 pop-up satellite tags to assess annual movement patterns. And these collected information on depth, light, temperature, and some of them also contained sensors for the magnetic field and acceleration. So we had them timed up. We had 10 timed to pop up in the winter when we expected they might be outside of the marine protected area on a spawning migration. And then 15 were timed to set up the following summer so we can get an idea of annual movements. So in 15 of those animals that received the satellite tag, they also got implanted in them an acoustic transmitter, and we tracked them every other week for 2 months in the summer of 2013 and again in June and July of 2014. So for the methods for the summer, we were looking at the proportion of fish that had home ranges and what was the home range size for those. And we used the exact same methods that we used for chapter 1. So the mixed effects model with the intercept only. And this was all based on acoustic tracking. Then for annual movement, we looked at seasonal displacement. So was there a difference in displacement between movement from summer to winter versus summer to the following summer? And to do that, we looked at all the tools we had available, which were our pop-up locations, fisheries recaptures, and the acoustic telemetry. And then another way that we looked at annual movement was to infer on each day whether the fish was inside or outside of the park. And I don't have time to go into this in too much detail, but basically we relied on unique oceanographic and bathymetric properties of Glacier Bay compared to the adjacent areas. We had the temperature data within the bay in our study areas. We could compare the fish data to that. And we also, thanks to Bob Stone of NOAA, had temperature out in the Gulf that we could compare it to. So using that data, we inferred continual residence or seasonal migration. And we used this to calculate the proportion of residents versus migrants, determine migration timing, and whether it was return migration. And so this analysis was based just on the PSAT data. So here's some of the results from the summertime movement. And here, each color is, where's my cursor? Okay, each color is a different animal, and the size of the circle corresponds to the uncertainty in the telemetry location. And what we found was that 12 of these 15 fish had home range behavior, and the population movement radius that was estimated was 485 meters compared to the 400 that was measured 20 years ago. And this was within the 95% confidence interval of the first paper. The ranges of the individual fish was almost exactly the same, ranging from 0.1 to 1.7 kilometers. So very similar. And then 2 of the 15 fish, we tracked them, but they weren't in the study area. They moved more broadly around the study area. So in terms of the annual movement, we had 21 fish that gave us pop-up satellite tag. And 15 of those were in the marine protected area year-round. But there were 6 that left all in December, and 4 of those 6 had returned to Glacier Bay by mid-March. One of them we found with the acoustic telemetry was within 1 kilometer of its release location the previous year. And so one of the 6 was recaptured outside the marine protected area on March 9th, the second day of the fishery opening. And then one of the 6 we simply don't know its fate. But when you look at the displacement over time between summer to winter and summer to summer, there's really not much difference. What I'm showing is the graph with displacement on the Y and your winter or summer on the X. And even for fish, even including fish that we know had migrated and come back, the median displacement was still under 5 kilometers for both summer and winter. Now, for looking at the results in terms of movement and migration relative to the commercial fishery, I am showing you this graph shows the proportion of fish that were inside the marine protected area on each given day. And you can see it starts to dip in December when the fish are migrating out. Now you overlay that with the timing of the commercial closures in the whole area. There was only about an 8-day period here where tagged fish were vulnerable to capture in the commercial fishery. So, in discussion of that, this study confirmed the finding of very small summer home ranges, less than 1 kilometer. And it demonstrated a cognitive ability to navigate to specific locations. So we knew that fish are capable of leaving the bay and then returning to within 1 kilometer after completing a spawning migration. We also have evidence of partial migration at small sample sizes, but still that most of the fish didn't leave. So a high proportion of year-round residents. But this has implications for marine protected areas. Glacier Bay, when the commercial fishery is eventually phased out, should be a refuge for adult fish, whether they're migrants or not, based on the combination of spatial fisheries closures during the summer and the temporal closure of the commercial fishery in the winter. So here's another way to summarize it. Glacier Bay fish appear to be big-time homebodies. Big time. But we really need information from other regions, other habitat types, other sizes and sexes of fish, and over multiple years to understand how to interpret this data in the context of halibut overall. Because if it's really something that a lot of them do in other locations as well, then there's some implications for their management. So site fidelity, we found small spatial scales and long time scales, and introduced the importance of understanding the attributes of the home ranges. What makes it worth coming back to a place like that? And then is there a vulnerability there to a certain type of habitat disturbance, or will they be more vulnerable to pollution coming back to a site that's polluted? It also has implications for spatial structure among adult halibut. This should be assessed with stock assessment, and understanding the potential value of closed areas for protecting spawning stock biomass. But we also need some additional tools to get the full details on the migrations. I mean, we found, based on the unique properties of Glacier Bay, we were able to determine the residency and the migration timing, but we couldn't tell where they went to spawn, and we couldn't tell migration pathways. So there's other methods needed to understand the fine-scale movements of these migrations. And such methods are geolocation models. So I'm switching to that for our chapter 3. I'm going to be telling you about how we can use archival tag data to reconstruct movement paths of fish to get that detailed information. So in general, a geolocation model, this is our chance as a scientist to be a detective. We've got the tag data, we've got the maps of the study area. We need to use those to infer from between the release location and the recovery location what is the path that the animal took, and some evidence of uncertainty for each of those locations. So that's reconstructing a movement model based on archival tag data. So for the demersal fish, I used a hidden Markov model, and this is a discrete state space model. It was developed for Atlantic cod in the North Sea in 2008 by Martin Peterson. And since then, it has been used on just a ton of different animals, different locations, so it's a robust, flexible model. It's been used on halibut, salmon, and sharks. But a lot of the times when it gets adapted for different situations, no one checks to make sure if there's any sensitivities to any of the assumptions that have been made for this. So I'm just going to briefly tell you about the framework of this model. It consists of a gridded study area. Then the next component is a movement model. So in this case, it's diffusion. And then the third component is your data likelihood model. And this is the way that you take the fish data and you match it to the study area to see which areas are more likely to contain the fish. And so when you go to adapt this model, these are the things you have to choose. You have to choose a grid size. You have to choose whether you're going to use prior information. For example, we could use that estimate of diffusion that we got from the net square displacement in Chapter 1 in this movement model. Or you can also estimate it within the model. And then the biggest thing that you have to do is you have to customize this data likelihood model, the way that you link the tag data to the fish. For example, if you're a pelagic fish, then you can just use light-based latitude and longitude estimates. But that is largely not available for demersal fish. It's there, but it's not consistent. But for demersal fish in Alaska, what we do have is depth. We have strong gradients in Alaska. The information that we have on depth from the archival tags, unlike the light data, is really reliable. We can get it from both harvest recovered tags and the pop-up satellite tags. And so the likelihood for the demersal fish model is based on maximum daily depth. And so for that, you assume that the demersal fish contact the seafloor once a day. And by doing that, the maximum depth is what can then be linked to your maps of the study area. And then the beauty of this is that if you have other information, you can add it quite easily to this model. But for now, we're just going to focus on depth. And I'm not going to say much more about this model, but I have written all the detail you want and more, probably more, and an appendix to the dissertation. But what I will say is that one of the assumptions for the likelihood is that in each grid cell is a normal distribution. And okay, so this model was developed in the North Sea, which is pretty flat. And I wondered, will the heterogeneous depths that we have in Glacier Bay have any effect on its performance? And so I looked at model performance in areas with different degrees of bathymetric heterogeneity and different grid cell sizes and different ways of specifying the data likelihood. So within the process of specifying your data likelihood, there's a ton of little details that I'm not going to talk about, and you will thank me later. So for now, I'm just going to focus on bathymetric heterogeneity and grid cell size. So we chose 3 study areas with different depth characteristics: flat, sloping, and heterogeneous. And here they are. For the flat, we looked at Norton Sound. So in all these areas, we had high-resolution multi-beam data. So we have the known depths for the fish, or the simulated fish. And then for the sloping area, we chose a data set that was in the Central Gulf. And then for the heterogeneous, we chose a data set that was from Glacier Bay. So the way we go about this is we simulate 100 trajectories per area. And this is an example of how we do that. We have our high-resolution bathymetry. This black line is a simulated movement path. We got it by generated with a random walk with 200 steps. And at each step, each of the 200 steps, you extract this high-resolution bathymetry, and then you add measurement error to it and tide data. And then you run it in the model. You run it in the model with different treatments. So we had 5 grid sizes and 9 likelihood models. And this is what it looks like when you run the model. So this is with a 200-meter grid. And you have in the black, you have the simulated track. And the yellow is what the model estimated. So it's really pretty good, I would say. And then compare this with the 1,000-meter grid. So you have it's the same trajectory, but now the model puts the movement way up on the side. So there's a little less performance on this model. And to look at performance, we looked at accuracy and coverage probability. So was it within what we think the error is? And I'm going to show you an example of that. So we're now zoomed in on that simulated trajectory. we're looking at one time step of the model. So the true location at that time step is in the pink, and the estimated is in the green. And this yellow indicates the grid cells that hold 80% of the probability at that time step. And so the absolute error between these two is 790 meters. We figure that out for each of the 200 steps and average it, and that becomes our metric of performance. It's the mean absolute error for that trajectory. And then we also look to see, is the true location within our probability, our estimated probability, so within this yellow polygon, and yes, this one is. So we look at the proportion of those for all the 200 that were within. And so this is just an example of a larger scale. So it's a larger distance between the known value and the simulated at this time step. And in this particular instance, the known was not within our 80% probability polygon. Whew. Okay, so that's the methods for that, and these are some of the results we're showing you for the accuracy, so the mean absolute error. So for within each grid cell, the performance was ranked, and the highest performance is in yellow, and the lowest is in blue. And what you have is you have your grid sizing increasing from 100 at the top down to 2,000 at the bottom. You've got your heterogeneous area here in the left, the sloping in the middle, and the flat on the right. And in between them is the different likelihood combinations that I'm not going to talk about, but there's it's likelihood specification information. But the thing I want you to realize is that the trend for performance was so it starts high in the heterogeneous areas and the small grid sizes. But as you go to larger grid sizes, the best performance happens in the flat areas. So the largest grid size, the flat areas performed better. And the same exact pattern is true for the coverage probability. So yes, there are differences in performance based on the degree of heterogeneity. We had the best performance in the areas with the highest heterogeneity, and that's because you have much stronger gradients there. But we had the worst performance in the heterogeneous areas too, and that is because at the larger grid sizes, you lose the assumption of a normal distribution within those cells, so they become more skewed. Whereas flat areas had a consistent performance regardless of grid size, and they also had a normal distribution. So another result that we recovered, that yes, there's differences in performance by heterogeneity and grid size for our error estimates, but the big thing is that every single one of them was low. They're all lower than we think, and whether that's an artifact of my simulations or something that we should consider for model performance elsewhere should be looked into. So in discussion, I guess my work points out that adapting a hidden Markov model is not a trivial process. You need to understand your geolocation variable, your study area, your fish, in relation to what the assumptions of your model are. That will help you pick the best parameters, and it will also help you have confidence in your results. And this is particularly important as there is a rise of black box software. And so in this case, you can give your data to, for example, wildlife computers, and it will pop out with a beautiful track and a beautiful error estimate. But you can't choose some of these parameters that maybe you should customize for your fish. And so you never really know how much confidence you should have, because as we know, all models will give you an answer, and they will give you a very nice answer. And it looks great, but you have to do some of the footwork to make sure that, that you believe it. And so the hidden Markov model is a promising a method for looking at the movement of demersal fish in Alaska. And this gives some guidelines as to how to use it, and the model is now developed for it. But it could be perhaps improved by the addition of different geolocation variables, such as the geomagnetic fields. And with that, we're going to transition into the last chapter, Chapter 4, looking at whether or not information on the Earth's magnetic field will help improve geolocation for demersal fish. So here is the Earth's magnetic field. It's three-dimensional. It can be modeled. It varies in space and can be modeled. And the SI unit for it is the coolest unit ever, which is the nanotesla, named for Nikola Tesla. And today I'm going to be talking about just the total magnetic field. So that's the vector sum of all the three dimensions of it, or you also hear of it as intensity. But the intensity increases from about 30,000 at the equator to about 65,000 at the poles. So the objective of this chapter is to determine whether adding geomagnetic data to the hidden Markov model improves the model over depth alone. So this is what the magnetic field looks like in Alaska. So you have intensity that is, or magnetic field strength that is increasing on a gradient from the southwest to the northeast. And you have magnetic field gradients that are decreasing over that same direction. And this alignment of gradients would be really best to detect movement for fish that is moving along from the Aleutians all the way up the coast to something like Prince William Sound. But that is not the only thing going on here. There are differences in what the tag would measure compared to what the model value is, depending on where you are, and there's geological structures, such as all the volcanic terrains that we have in Alaska, that can really change the magnetic field in that area. These are called local magnetic anomalies. And so on the graph on the right, these are all showing differences from this model, the main fields on the left. So definitely in Alaska, we have to think about these magnetic anomalies when we're using the magnetic field. And the magnetic anomalies are hard to map. They're small in spatial scale, sometimes really small. And so we made our own fine scale map in Glacier Bay. We had a magnetometer strapped to the bow of the aluminum vessel, and while we were doing our tracking of fish, we were also measuring the Earth's magnetic field every second. So we got a lot done. And we also made a fine scale map of the magnetic field in Glacier Bay. And so what you can see is there's a couple of areas there that are really high intensity in the center. And just to put these in perspective, near Kodiak, if you go, so basically the extent of Kodiak, 250 kilometers, the change in the magnetic field is 1,000 nanotesla. But if you're in Glacier Bay, you can go 1 kilometer and you're changing twice as much. So really strong gradients there with the anomalies. And the existence of this fine scale map led us to some opportunities for a small scale case study to see if, so based on using this fine scale map as our known value for simulated fish, whether the performance would improve, compare it with the fine scale map, but also see if it provides good performance with the coarse scale map, which is available over a much larger area. So now we're zooming into our data sets that we have. On the left is depth, the most informative gradient that we have at our disposal. And then we have two maps of the magnetic field, the one that we made in the center, and the one on the right. This is basically a combination of, if you were to add the two, the main field and the anomalies together, this is that map. So we've got it over a big chunk of Alaska, but it's at it's a coarser map and it's at a coarser scale. So our approach here was to simulate 1,000 random trajectories, just like we did in the last chapter, except now we're extracting depth and magnetic data from those. And we added magnetic error at 4 different simulated tag resolutions, just to understand what the effect was with different magnetic tag resolutions. And we run the hidden Markov model on the simulated data with the different likelihood treatments. So the treatments were depth only, and then depth and magnetic. And within the depth and magnetic, we had 2 fine scale map options. Again, I'm not going to explain the details of what makes these different. And 4 coarse scale map options. And then we ran the model on those, and then we compared the mean absolute error as our performance metric between the depth only and the depth plus magnetic combinations. There we go. Okay, and here's the results, and it's a big gnarly box plot. So first, all the different treatments are separated by the black lines, and the depth only is on the far left. The ones that use the fine scale map are the next 2. They're in the yellow box. And the ones that use the coarse scale map, which has the wider applicability for all of Alaska, these are on the far side. And within each of these treatments, you have at the very bottom, the V is very high, H is high, the M is medium, and the L is low. So these are your simulated tag resolutions. And I don't want to spend too much time looking at the exact qualities of this map, but just realize that wherever there's a blue arrow, those treatment combinations were better than depth alone. So they improved the hidden Markov model by the addition of magnetic field data. And so most of the fine scale maps did too, but the important thing is that there were some with the coarse scale map that did as well. So this is encouraging. However, now pointing out with the treatment that's circled in red, this is what you would get if you just use the default method of specifying the data likelihood. And it just brings home the point that you really have to understand what you're doing with the data likelihood, or else it's going to be worse. So this is worse than just depth alone. You'd be better off with just depth, but you're not going to know this unless you look into it a little more. So in terms of the results, yes, the geomagnetic data based on these simulations has potential for improving depth-based geolocation, and that's good. So the coarse scale map, there was improvement as long as you specified the data likelihood correctly, and as long as you had tag resolution that was adequate. And the fine scale, it was better as long as you had tag resolution that was at least medium. So, and the best performance was with, unsurprisingly, with the best map and the highest resolution of tags. So, but in general, high resolution tags get you a better result. Unless the highest resolution didn't add that much more to your results than when you're working with the coarse scale map. Okay, so in discussion of that, it seems like it's a promising technique. And putting it in the hidden Markov model is really, I think, going to be important, because when you buy the tags, they come with software, and that software is not going to be appropriate at all, because it requires that you have light-based longitude, that you intersect with the magnetic data to come up with an estimate. And if you don't, like most fish don't get light, you basically can't use this method that comes with the tags. And it doesn't account for magnetic anomalies at all. So putting the geolocation data into this hidden Markov model that can deal with those things is going to be a really valuable approach just in general. It allows for understanding map error in relation to anomalies. But the big thing is that it actually provides a lot more information on where the fish is, as long as based on our results. So we had improved performance in Glacier Bay. If you were just looking at what was available with just your regular main field without the anomalies, there would be no information from the magnetic field to go on. There's just no change in that. But the anomalies made it so that it increased the value of the hidden Markov model. So all this is encouraging for use within other regions as well, particularly in areas where there is not depth gradients. And so in those cases where you have geomagnetic but not depth gradients, it would be expected to be really helpful. So, but there's some caveats, and this is, it's still pretty much early stage here. What we've done with this is we've demonstrated a theoretical basis that they could be very good for geolocation. But it really, what we found is it really kind of depends on the tag data. And there are some tag improvements needed. And I didn't have time to go into any of that at all. And it would take another hour probably just on the tags themselves. But basically there's some improvements that need to be made. And when those are made, then they need to be deployed over a broad area to look at the differences between what they measure and the maps in those areas. And it's particularly important to look at the values on the seafloor because sometimes the anomalies are stronger, or they could be stronger right on the seafloor compared to on the surface. So get the tags so that they are measuring what you need, and then put them out on a broad area. And then the other thing I didn't talk about was temporal fluctuations. Now solar storms can also potentially be recorded by these tags, and so you have to incorporate that into your study design. So there's a lot going on with this. It's really not a simple method. Depth is much easier. But for fish like sablefish, they need this. They need this. They've got depth, and that's it. So in terms of the overall contributions from this dissertation, there were two main ones. The first is providing tools to understand movement of demersal fish at multiple scales in space and time. And the first is the net squared displacement from chapter 1. That was a tool that you can, I used it for small scale analysis, but you could look at large scale analysis too. Then there was the method of double tagging fish with both acoustic and archival tags, so you could get that small scale information and for the same animal understand its larger movements. That really helped give insights into particularly the site fidelity. And then the hidden Markov model is a tool that can be used at either the small scale applications or larger migration. The other thing is, in addition to tools, it's insights into Pacific halibut movement. Our studies show adult site fidelity to summer foraging areas is pretty dominant in Glacier Bay. So it's very small spatial scales and very long time scales. And we also discovered evidence of partial migration. So not all fish undertake migrations. That's going to be important to figure out more why and what the population proportion is for that. But in general, this adds to the literature that suggests that behavior of the fish is perhaps the basis for possible spatial structure in halibut populations. So what are the implications of understanding this type of behavior for demersal fish overall? Well, it really leads to a mechanistic understanding of movement and behavior. So for example, if you know how and why the fish are moving, then you can understand how temperature might change foraging or spawning locations. You might, if you know where the pathways are, you might be able to avoid them to avoid bycatch. It has value for understanding timing of fishery and stock assessments relative to migrations. For example, Pacific cod and the Aleutian Islands. So they're assessed in the summer when they're foraging, but the fishery occurs in the winter when they're spawning. And so understanding the migrations relative to those two things is really important. And I'm working with a project with Suzanne on that. And also just general information on how you manage versus time and space. For example, how do migrations affect how many of Canada's halibut we're catching? So lots of ways we can use the data. But one of the big things that I want to stress is that with electronic tags, you get a lot of really valuable movement on individuals, but it's going to be a challenge in the next year to ramp this up to implication for populations. And so you can either do that with methods that combine multiple tags instead of just looking at single, and that might be putting multiple animals in one hierarchical model, or it could be, I was thinking about this the other day, you could just do the geolocation on a number of data sets and then use the net square displacement analysis to quantify and get that population estimate of extent and timing. But perhaps the biggest thing is going to be integrating the detailed data with other tools such as genetics, otolith chemistry, and conventional tagging. Okay, that's all I had planned for you today. I want to send special thanks to David Stone from UIF and Morris Tybee from Woods Hole. These really help me understand the ins and outs of the magnetic fields, and so their help is much appreciated. And then, in addition to the funding and our committee, there's just a ton of people that helped out with this project over the years, and so I'm very thankful for that. Some of them in this room. So thank you. I also want to take a minute to thank Gabrielle and Chris and the support staff here for helping me through my time here, and I'd also like to thank Alan for putting up with me for some crazy late nights. Okay, that's it. I can take questions now. Yeah, perhaps, is there something from the distant sites?
Guess we'll take it from here.
Okay, should we take some questions here? Yes, Yumi.
Great job, Julie.
Thank
you. I was really surprised to hear about such site fidelity and small-scale movement in Glacier Bay, and I was wondering if there is other evidence of that from other places in the Gulf of Alaska or really anywhere, and if not, I mean, is there something special about Glacier Bay?
Well, so that's the thing, and a part of it is that the tools haven't been available to really find that out. So some of Tim's work and Andy's work has shown that, yeah, you can tell with the satellite tag data that they're leaving and coming back, but you don't really know what's going on with the detail that we were able to get with this. So yeah, it adds to information that just wasn't able to get at the resolution that we were able to get. So there is from other places in Alaska too. I suspect that I suspect that there are probably differences though with habitat, because Glacier Bay is it's patchy, and you worked in there as well. But yeah, it's really got valuable habitat there too, and part of the reason to have a place that you want to come back to, you would think it would have to be valuable. So that probably has some impact on where you observe it and where you don't. Yes, Sherry.
Kind of related to Yumi's, but the surgical implication of those tags, does that limit you to the size, and did you generally choose the same size halibut and gender?
Yeah, so the inference here is for adult female in Glacier Bay. Both the studies were very similar sizes. And so you're right, there's probably, within Glacier Bay, there could be differences with smaller fish, certainly. But what we looked through the lens there was adult fish And in thinking about management implications, having understanding of what the adult females are doing, because they're mostly females when they're large, is probably really important for the fisheries management aspect of things too. Yes, Jen.
What's happening with the fish that are staying through the winter?
They go deep. They go, so in the summer they're shallow, but in the winter they have a shift towards deeper water.
So change in habitat, but staying in the same
bay.
general site. Huh.
Yes, Francis.
You said that adding the magnetic information into some of the models. Do you have an idea of how much that is?
Well, it's kind of hard because it's all, I mean, it's not, the best improvement was when we had the fine scale map and the high resolution tags. In that case, the mean error dropped from something like, I'm trying to remember the numbers now, but it dropped substantially. The other, so the best performance was with the high, with the best map. And so even though there was improvement with the coarse scale, the magnitude wasn't that great, but the important thing is that it was there, and that you're going to, and when you use it in other situations, so perhaps you're in an area where the magnetic anomalies are quite, the range in them is much larger than in Glacier Bay, because they have, in Kodiak, so the anomaly gradient in Glacier Bay was about 2,000, going from one value to the next in a kilometer was 2,000. There's huge swaths of anomalies in Kodiak that are 4,000 nanotesla, and so in that situation, I would expect that even that there would be a lot more. When you have a lot more gradient in the magnetic field, you would expect the improvement to also correspondingly improve. And so we're just limited to what the gradients we had to work with in Glacier Bay. So there was improvement, it was slight, but it could be different in areas where the magnetic anomalies are greater, or in areas where, like I said, the depth gradients are shallow. So in that case, you could see a lot better improvement. If you get an area that has high magnetic field gradients and low depth gradients, then you're going to have a lot more improvement in your model. Does that answer? Okay.
Yes.
Thanks, Jamie.
Great job, Julie. I was curious, in your first chapter, one of the behaviors that you quantified was a home range shift.
Yes.
And I'm interested in learning more about, was there a threshold or range across those individuals where that shift occurred, and what might drive that shift?
Oh, yeah, that's a tough one. I didn't do the population model on that because there's actually two. There's that I modeled. There's the shift there, and then there's a one where you're going farther and then you come back. So off the top of my head, I just can't remember. It's been a while. Yeah.
Related to that, you said you thought you had evidence for partial migration, but were you able to distinguish that from just sort of a continuous variation in migration distances? And some would be, how you define a migrant, some would fall on one side of the app versus the other.
Yeah, so I guess I'm just defining it as 15 of them didn't leave the marine protected area to go on the spawning migration. Yeah, there's all sorts of stuff that I didn't go into, such as the reproductive evidence that we have. So the ones that left Glacier Bay, we could see in their depth records, half of them. So we had 4 detailed data sets, and we could see them spawning. We had 9 detailed records from within Glacier Bay, not a single spawning rise to be seen in that. So, I mean, that's, it's kind of, it's just kind of an observation that it's there, and then we just don't know, aside from that, more than how to start characterizing it in terms of those
So
things.
maybe more just related to their life history choices at that time, and not necessarily fish has always been a mover.
Yeah, that's why we also need multi-year tags. Yeah. Yes.
What kind of depth are they spawning out?
Well, so they weren't that deep. A lot of the spawning activity that Tim and Andy have uncovered has been like at, what, 400 meters? So this was 150, 200, the ones that we found. So that in itself is just kind of like, because you use the depth as part of your.
Yeah, that's the shallow end of what we described. It's from sort of 200, maybe 180 down to about 800 or so.
Okay. Yeah, so these were about 150 to 200. Yes.
So, kind of following up on Megan, could you say that a somewhat large proportion of the population is not spawning each year?
Well, so that is an important question. It's possible that there's just a different behavior that's not a spawning rise. And I would like to look into that with acceleration tags, because if there's something that, I mean, it's possible that is, the spawning rises are something you do when you undertake your migration, but maybe there's another behavior that you have when you stay home. So that would be important to figure out, and I think you could do that with accelerometer tags, so that would be kind of tricky. But I think that some people have told me that they have evidence of catching fecund females in Glacier Bay. But so perhaps they're spawning there, and it's just a different thing that we can't detect with the spawning rise. Or else, if they're not spawning and 2/3 of them, small sample sizes, I have to be careful of that. But some proportion of them aren't actually spawning, then that's important information for stock assessment.
Would it be easier to look for eggs or larvae or juveniles settling?
Yeah, probably. Oh, come on, Franz, I want to put accelerometer tags out there. Oh, shucks. Rats, there goes my next proposal.
I'm just curious how the technology has changed for tagging in the short duration of your PhD.
Oh, in my PhD.
Short.
That was short. Yeah, well, there's always constant changes. I mean, like the satellite tags or the acoustic tags?
Yeah, the acoustic tags.
The acoustic tags.
They're getting smaller.
Well, I'm sure they're getting smaller. At a certain point, I haven't been doing any recent research since 2013. So you kind of lose track. But the trend is for them to get smaller because you want to put them in smaller fish. And I'm sure there's all sorts of things like new bells and whistles, like chat tags, like you can have other fish swimming around that'll just receive signals from other tagged fish. So there's a lot of really interesting developments with just the types of acoustic telemetry rather than being in your boat and having your hydrophone and hearing it. Yeah. I think a lot of people are doing stationary arrays.
Are you working with any of the tag manufacturers to improve the geomagnetic component of those tags?
Yes. Yes, and it's complicated. Yeah, I have them back at my house. I have my little containers that I go into the muskeg where there's no interference in the magnetic field. I have the dog walkers all walk past my magnetic testing station on there, but yeah, so I do. And yeah, I guess I can't really go into it without describing some of the issues, but yeah, it looks promising. It's complex. They're complex sensors, and there's depth that changes a whole number of things that if you don't know to expect it can lead you to a result. Yeah.
That's it? Did you want to say anything about tonight?
Oh yeah, so tonight we're having a bonfire at Doug and Rob's, and I'm embarrassed to say that I don't have their address.
It's a mile before Bonnie Bright Town off. They pull out, but they just built a.
Oh yeah, so there's that. Yeah, so they built the
It
steps.
used to be the free candy town.
Free candy during.
6250.
Oh, 62,250 North Douglas.
Okay, 62250 North Douglas. We're gonna have a bonfire, and Alan's getting some pizza, and anyone is welcome.
What pizza on a stick?
Yeah. Yeah.
What time?
Oh, 6:30, I think. I don't know. I'm assuming I'll be done.
According to the text.
Okay. Oh. Wow, somebody's more informed. Excellent. Yeah, so if you can come, I'd be glad to see you there. Okay. Thanks, everybody.
Yeah. What's that?
I'll be back.
Doing good, how are you? Good to see you.
I'm wrapping up my master's.
Yeah.
My
Sounds good. I'll be waiting for anything.
You'll wait. You should do other things in the meantime. Hi, Sherry. How are you doing?
I'm good.
I know.
You can get very far away. The road only 20 miles away. Exactly.
Oh my God. Been a long time coming.
And she said yes, and she was serious about it. I thought she was going to say no, I just think
Yes. Oh, good. Would that be helpful? Yeah. Yeah, okay.
I'm trying to finish up my master's work.
I didn't read the article.
Yeah.
So I was wondering in the summer if you would be available and then maybe I don't know how this would talk about potentially if you want to I kind of changed around after I talked to you the last time. You mentioned how you did a smaller scale study where I could retrieve the details before you did the big scale. So I was thinking of doing that, or maybe more somewhere local.
Yeah, well, I'm glad that
you're improving the tagging.
I forgot to. Shoot, that's what maybe what Sharon's getting at. Set around here. Oh yeah. Okay, that's right.
I think there's more events than
Oh yeah,
Well, we hit a lot of stuff.
Yeah. Yeah. And also
yeah, I'll let you know. I got a few things to get through first.
Basically how great They are, but you know what their big business is acoustic releases for voice. That's how they it's not official. So yeah, and they've been making those acoustic releases for a long time. And they make good acoustic releases for these other companies do. They make good acoustic releases. Yeah. Exactly. And that's how they and they do have so to go a couple of years ago, so there's a lot of freshwater researchers there, and it was amazing the amount of people that use desert star tracks at Great Lakes because they have no choice, and they're using one like sturgeon, and they really were about sturgeon, and for really similar things like Glacier Bay research of like should we close this bay off during sturgeon spawning season? Are they staying there? Are they moving outside? They have a lot of similar questions. They every single person owns a goniometer, and none of them got data back. And so they're essentially a tag that releases with a radio beacon on it, and you better go find them. Exactly. Yeah. So they are an archival tag that pops up with a radio beacon. They're not a satellite. I thought you were Nope. Nope. And you know the scale of sturgeon movement in relation to the scale of a bays, a lot of people were getting 50 to 75% recovery just with the use of a goniometer. And then there was a couple. Exactly. Yeah. But the goniometers are so sensitive, like you make a visor. Right.
all the ones that live there. Those are all, yeah.
Nice.
So you guys are gonna grill for now, right?
We're gonna ask questions.
How long do you expect it to take?
So
Hour?
it usually takes, I'd say average 2 hours plus or minus 30 minutes. Sometimes they extend to 3 hours.
All right, we'll go easy on it.
Yeah, we will.
Yeah, thanks you guys.
Thanks for everything.
Thanks for coming. Now my God, here we clean up the closets.
No, from now. Yeah. And it depends. I don't know. I mean, some of them might take some she's basically and then that ended 5 years ago, and now it's like I mean, normally I walk out of here and I have like 2 pieces of paper like this full of questions. Hey, Mike, I don't know if you can hear me above the din of the background, but we're gonna probably take another 5 minutes off and then reconvene. Okay, thanks, Mike.
Now we got to No, it's been nice. I was like, you know what? Yeah. I have some stuff downstairs. I'm like, I can sell or give away all of it.
So we'll take like 5 minutes off.
Okay.
Where we here.
And also.
I just let Mike know that.
Yeah. I'll think about some cool prices. You can't have this fun.
This one's gonna be opportunistic. I'm probably going to be myself. My day is gone. Wow. Yes. I will see if my child is up for it. We'll try to work here soon. Maybe 10 minutes. Okay. That might be our last, as long as we can last. But okay. So, okay, sounds good. I love for kids. I didn't know where that is. Okay. Good. Awesome. I hope to see you there. And enjoy the rest of the process. Okay. All right. Thank you later. Oh.
Very, very, very professional, as always.
Thank you.
I think they're gonna go easy on it. They're gonna go. That's my guess. So, were they all good?
That's Milo.
Ah,
Milo, this is my husband, Alan.
Hey, Alan.
And my friend, Mark.
Nice to meet you. Thanks for helping me.
Nice to meet you. Yeah, we're gonna go easy on her. Definitely.
The statistician. My advice was to say, I know more about this than you now, so don't bug me. But apparently that's not
PhD
how
is
it's
all
done,
about.
isn't it?
Yeah.
She's fine.
All right, I'm gonna take a chance to visit Albano.
Congratulations, Julie.
Thank you so much, Mark.
Yeah.
I'm so glad you came.
Yeah.
Can anybody there hear me at this point?
Yeah, this is Milo Atkinson.
Yeah, hi, Milo. I just got a message flashed up on the screen here that said that this will end in 5 minutes unless it's somehow extended, and I'm not familiar with how this all works.
So that's pretty typical. Right now we're connected to about 6 or 7 different places.
Okay.
And usually what we'll do is disconnect and reconnect for the participants.
Okay,
So,
that's fine. Thanks. Same contact, same password and all, right?
Yeah, it should be.
Okay.
So do I need to do that as well, Milo? I need to X out and then reconnect?
Yeah, I suspect so. That's typically what they do is they do the public presentation and the defense is separate.
Okay, got it.
Oh, so people can't spy on it.
Yeah.
Can't log in and break in and see what's going on. Yeah.
All right, so I'll disconnect then and connect back in.
Well, yeah.
That make it 2:30?
Yeah, so do it after 2:30 because I bet you they have it set to disconnect to end this session at 2:30 and restart immediately after. So you can disconnect now and then after 2:30 reconnect.
Okay.
I'll do that. Sounds good.
Likewise.
Thank you. Tim and I might be stuck in Juneau, Milo.
I was thinking that, yeah. Yeah, well, they had a big dump last year and they seemed to keep the airport open pretty well.
You are the only participant in the conference.
In the north, like when I fly over Syracuse, Syracuse is never the problem. It's all just a matter of whether or not the planes come from other places to get to Syracuse. So at least as of 5 or 6 years ago, our airport still owned the world's largest snowplow.
Ooh, okay.
Like our planes carry salt and the world's largest snowplow.
I like that.
Your call will be disconnected.